Hello everyone, thanks for participating to this presentation. First of all, let me briefly introduce myself. My name is Efecan Kor. I'm a graduate student in civil engineering at Ozcelik University. Today I'm going to present our study named Incremental Dynamic Analysis of Concentric Express Frames designed to TBC 2018. And I want to thank my advisor Dr. Yigit for his mentorship and participation in this study. First, let me start with the outline of the presentation to provide a general idea on what I will go through today. I will start with a brief introduction and the motivation of this study. Then I will continue with structural design and nonlinear model development. Afterwards, I will explain the analysis procedure and related results. And finally, I will sum up with a conclusion. So let me start with the introduction. Concentrically braced steel frames are commonly preferred lateral load-resisting systems. In figure, there are three types of CBF systems. The first one is X-braced frame, which is the main focus of this study, and the second and third ones are chevron and V type braced frames. The load distribution between the members of such systems are basically based on truss action, which means the shear force acting on each story is shared between the braces as axial loads. And during higher level of earthquake events, the energy dissipation is ensured through the brace buckling and brace yielding under axial compression and tension respectively. And accordingly, inelastic deformation demands during major events should be provided while maintaining the general stability of the building. And to avoid potential plastic mechanisms, the members except braces must be capacity designed. And there are also several design requirements available on seismic codes, national seismic codes or international seismic codes to achieve this goal. And the next topic that I want to express is Turkish Building Earthquake Code 2018, which was published in 2018 and superseded the previous one, the Turkish Earthquake Code 2007. And during this transformation, several changes had been introduced, such as response spectrum or earthquake load reduction factor definitions. Also, there are new concepts were introduced, such as yield mechanisms or expected material strengths, and these yield mechanisms are shown in this figure, which are similar to the ones in AISC specifications, and all these changes are expected to affect the CBF designs. So this led us to the next topic, which is the motivation of this study. As I mentioned just before, transformation from the previous code to the new one has introduced several changes in design procedure. So this situation can be expected to design approach and loads, and accordingly it can lead to possible differences in CBF design. Thus, this study aims to understand and present the seismic behavior of X-braced frames designed per TBC, and to that end, a two-story X-braced steel frame was designed in accordance with the requirements defined in TBC, and it's analyzed using IDA procedure. And now I will continue with the structural design. We have a 40 to 30 meters floor plan with 5 bays in each direction, and 2 out of 5 bays are braced bays, which are shown with thicker lines. Also, there are 2 stories with 4 meters constant height, and the design parameters and loads of the building are as following. The design level response spectrum of the building is provided in this plot. The marked point on the curve represents the elastic design spectral acceleration, and the final sections coming from the design are shown in here. Double sections were used for beams and columns, and HSS sections were used for the braces. And after the design procedure, it comes to nonlinear numerical model, which was developed on OpenSea software as a 2D model. All members were modeled as force-based nonlinear beam column elements consisting of fiber sections, which means the distributed plasticity approach was adopted, and the steel O2 material was used for all elements, which is currently available on platforms library and follows a hysteretic model. Also, all connections were assumed to be simple connections, including the column bases. Also, linear columns were implemented to the model in order to affect for and in order to account for the p delta effects, and also to simulate the buckling behavior of the braces. The brace model proposed by Ulis was used, which suggests placing an initial camber at the midpoint of half brace length, as drawn in this figure. As I've just mentioned before, the brace model proposed by Ulis was adapted to model the brace elements of this study. In this approach, each brace element is suggested to be divided into 4 connected segments with initial cambers of 0.1% of half brace length, which are assigned at the midpoint of each half brace, as it is also illustrated in this figure. There's the half brace length and initial camber. Also, it can be seen that this model represents the second mode buckling deformed shape of compression elements, which are restrained at their midspans. The purpose behind this is to be able to account for the post-buckling behavior of each individual brace element. And validation of the model was made with the experimental study by Palmer. In that study, a full-scale single-story, single-bay express frame was tested, and we simulated the experiment with the same parameters using our analytical model. The comparison between the results of this test and our analysis is shown in this figure. It can be deduced that the model captures the general behavior of the experimental study. However, it underestimates the base shear, especially in elastic region. But in general, the numerical model was deemed adequate for the purposes of this study. The next chapter is analysis part. After constructing the numerical model, the design system was analyzed under a set of ground motion records. The incremental dynamic analysis procedure was adopted as the nonlinear dynamic analysis method. This analysis approach is an effective tool to observe the relation between structural response and versus ground motion intensity, and to understand the dynamic capacity of a structural system. In this method, the design system is subjected to ground motion, which is scaled up incrementally at each analysis step until a limit stage is triggered. This is, of course, a brief explanation on IDA, which is described in detail in the study by Van Watstikos and Cornell. Also, limit states can be defined in terms of damage or intensity measures. For instance, interstory drift ratio, base shear, or another damage indicator can be chosen as a damage measure, while peak ground acceleration or spectral accelerations can be selected as intensity measures. For nonlinear dynamic analysis, a set of ground motion records, including 12 separate records, were selected from the PRNGWS2 database to be consistent with fault type, fault characteristics, and site conditions. On the other hand, a typical 2% mass and stiffness proportional damping was assumed, since it's a generally accepted value. And this takes us to the results part. The given figure is a multi-record IDA plot that's constructed according to the results of IDA procedure. Each individual curve represents one specific ground motion with an increasing spectral intensity and corresponding maximum interest to drift ratio with collapse points marked on them. Those points were observed at the spectral acceleration value where at least one of the DM or IM based limit state or rule is achieved. The limit states chosen for this study are 5% of maximum interest to drift ratio and 80% reduction in initial slope of each IDA curve as damage measure and intensity measure rules respectively. And the horizontal dashed line indicates the median collapse intensity, which was calculated as 2.28 G, while the vertical dashed line is maximum interest to drift ratio equals to 5%. And based on the IDA results, the collapse fragility curve of the system was constructed as a function of collapse probability and ground motion intensity using a cumulative distribution function, which is shown in this plot. The points on the plot show the spectral intensity values that correspond to collapse probabilities from 0.1 to 1. From the fitted curve, the median collapse intensity of the system, or in other words, spectral acceleration at 50% probability of collapse, was obtained as 2.28 G. For this system, the maximum considered earthquake level spectral acceleration was calculated as 1.67 G from the response spectrum defined for the maximum GM intensity level considered in the TBEC, in the seismic code, and accordingly the collapse margin ratio of the system at MCE level was calculated as 1.37, and also the probability of collapse of the system at MCE level was obtained as 30%. And I would like to wrap my presentation up with conclusion part. In this study, it was intended to understand and present the seismic behavior of express frames designed per TBEC. Therefore, a two-story XPF was designed, modeled, and analyzed by adapting the IDA procedure, and the results of IDA were used to construct a collapse fragility of the system, which enabled to obtain several indicators that provide insights into seismic behavior of the design system. Also, the collapse probability of the system was calculated at 30% at maximum considered earthquake level. And as a general outcome, the designed XPF was found adequate in terms of its collapse performance. And that brings us to the end. I would like to thank you for your time. If anyone has any questions, please feel free to ask, and I will do my best to answer. Thank you.